In part 4 of this series, we'll find out how much force is being exerted on a dam that has this triangular shape. To do this, we'll have to use this formula where we have the integral between A and B for density times gravity times d of y times w of y dy. This is a given value, it's 1000, so is this, 9.8. d of y is the height of each individual rectangles that we use to find the area. And so this part right here is d of y, which is equal to y. This part is the hard part. We need to come up with a function that represents the width at any y value. Let's do the easy part first and fill in what we know, and then we'll find out what w of y is. Force is equal to the integral between 0 and 15, the height of this triangle, 1000 times 9.8 times y times w at y dy. This is our goal. We're going to find that next. To find out w at y, we need to use similar triangles. So I'm going to start by drawing out a triangle for you. And I know it's the opposite direction, but you can use your imagination. Our triangle has a width of 40, no doubt about that, and it has a height of 15. If we were to take a rectangle along here, we don't know its width, nor do we know its height. So we don't know the height of this triangle, nor do we know its width. But what we can do is compare this triangle's dimensions with the bigger triangle's dimensions. So I will compare this 40 with this width and compare this height with this height. Here's how. We'll take what we know, 40, and divide it by the width of this triangle, which is w. At the same time, we know the height of this bigger triangle, it's 15, but we don't know the height of the smaller triangle. Here's how I like to envision it. Pretend that this rectangle was down here. If that rectangle was down here, it would have a height of 15. Now, pretend that we have shifted it upwards. What has happened is that that 15 has gotten smaller. And it's gotten smaller by an unknown amount. So we're going to write down 15 minus y, that unknown amount. So the height of this is always 15 minus y. What we have to do next is find out what w is equal to. And we can do that by solving for w. I'll multiply both sides by w first, and then divide both sides by this expression. If I do that, I end up with the following. 40 over a quotient 15 over 15 minus y is equal to w. Rearranging this, I should end up with 40 times 15 minus y over 15 is equal to w. You can reduce now as well. Dividing 40 by 15, they're both divisible by 5, so this becomes a 3, and this becomes an 8. Our expression for the width is 8 over 3, 15 minus y is equal to w. What I'll do next is substitute this equation into here, where I end up with force is equal to the integral between 0 and 15. 1000 times 9.8 is 9,800. Y times 8 over 3, bracket 15 minus y, close bracket, dy. I can pull out 9,800. I can pull out 8 over 3. Those don't need to be integrated. That'll leave me with 9,800 times 8 over 3. And then I'm left with y times 15 minus y, which is 15y minus y to the power of 2 dy. Instead of doing this manually, we all know how to integrate and find the antiderivative of these two terms. I'll use my calculator function. I click this button, type 15, alpha, my letter, it's okay that it's x, minus x to the power of 2. Now I put my bounds, and don't worry, I haven't forgotten about that. 0 to 15. That's the number that I get. Then I multiply it by this. Multiplied by 9,800 times 8 divided by 3. That gives me 14.7 million newtons. 14.7 times 10 to the power of 6 newtons worth of force. And so there you have it. That is how to express fluid pressure, force as an integral. Make sure to watch part 5 for our last example in this series.